Okay, so this is really our first chance to look at an actually indeterminate problem, like so we've looked at this in theory, but now let's look at it as if it was a problem we're going to solve. And so the question then is to solve for the reaction at B, and I'm going to step through it in in the same process that I would a more complicated numerical question, kind of to reinforce what we talked about in the theory lecture. So the first thing I need to do is I need to do up my free body diagram. And so I'm going to label it here to the right. I will do it here. And on that free body diagram, of course, I'm going to put my force applied, P, and then I'm going to put my two reactions in. So I have my reaction at A and my reaction at B. And I think intuitively I understand that they're both going up. So it works out really well. We'll get a couple positive numbers here as it works out. So when I look at this, of course, because this is a single dimensional problem, I only have one equation of static equilibrium. I clearly have two reactions. So I am short an equation in order to resolve what the reactions are directly. So that means that it's statically indeterminate to the first degree. So I need to be able to derive one compatibility equation to augment my equation of statics so that I can resolve for the two reactions. So the method of superposition, as we apply it, is we start off and we're going to have a primary system. And in that primary system, I am going to remove one of my reactions, which I will apply back later. But for now, I'm going to make it into a determinate system, which will be my primary system, by removing one reaction. So in this case, I'm going to choose to remove R at A, or the support at A. And so now in my system, I will have a support still down at B. So we'll have a reaction at B, but it won't be exactly the same as the original R at B. So I'm going to denote everything here with a prime to indicate that it's a slightly different value. We have our load. We're going to apply our load at this point, so P, but we don't have our displacement at the top, or sorry, we don't have our reaction at A at the top. And to this, so superposition basically says, as a reminder, that the original system is equal to the primary system plus what other systems we have to add to it. And those are our redundant systems where we apply back the reactions that we got rid of in our primary system, we apply them back as applied loads. So our redundant system, and so we still have, we're applying it back to the system that we had before. So we still have a reaction at B, and this one we'll denote with a double prime. We've already applied the load P, so we don't have to apply it again. But in this case, we have to apply our reaction at A, and we're going to apply it as if it's an applied load. And it would be equal to R at A. And so basically, when you look across the systems, they have to add up. So if I look, I have R at A in my redundant system. I don't have anything at that end in my primary system, so it adds up to R at A, which is in my original system. In the redundant system, I don't have an applied load P, but I do in the primary system, so it adds up to the P in the original system. And down at the bottom, we also know, based on what we're looking at, is that R at B is going to be equal to R at B prime plus R at B double prime, because it has to add up. Now we're partway there. The one thing we haven't done yet is we haven't figured out what our compatibility equation is. And so what we need to do is we need to look at the displacements of the primary and the redundant system. So I'm going to point very specifically to what our displacement will be at the end. Now, in most free body diagrams, we don't necessarily show it as shorter or longer. We've done that in some of the slides, but we don't normally. But we do know that there's going to be some displacement at A, and I'll give it a prime because it's on the primary system. Now, if I look at this system, I know it's going to shorten because the bottom half of the bar, the bottom portion of the bar, is in compression. And so it's going to shorten. The top portion of the bar is just going to be effectively a rigid body unloaded. So it will shorten, and we'll have a shortening at delta A. And then if I look at the redundant system, we know we're going to have a displacement delta A double prime. And just by inspection, I look at the redundant system, I see that it's the whole length of it is in tension, so we know it's going to elongate, right? So this is an elongation, and this is going to be a shortening. Now, just like RB was equal to RB prime plus RB double prime, we also know that our displacement at A is going to be equal to our displacement at A prime plus our displacement at A double prime. But we have one other bit of information. If we go back to our original system, we see that A is actually a fixed support. So we know that it won't actually have any displacement overall there. So delta A has to also equal to 0. And this is our compatibility equation. And it's in applying that using our displacement formula that we're going to be able to arrive at our reactions. So just a quick look, if I were to look at our primary system, quick method of sections, if I look in the bottom half, we know that that's going to be in compression or negative P. If I look in the top portion, it's not going to be loaded in any way, so it'll be 0. And the entirety of the redundant system is going to have an internal force of RA. So now all I need to do is to apply my compatibility. Okay, so solve for reactions. And we do that because we know that delta at A is equal to 0 is equal to delta at A prime plus delta at A double prime, which is equal to, and this is where we're going to recall that our delta is equal to our PL over EA. So in the case of delta A prime, our load, which we see from our primary system is negative P, times our length. Now, it is only applied over the length little b, and A has no load in it, so we'll put in a B here, and we'll divide it by EA. And then we go delta A double prime, so we're going to add to that, and the load in this case is RA. It's applied over the entire length, which is L, and we'll divide through by EA, and that's all equal to 0. And so we're able to isolate for RA and ultimately resolve that down to PB over L. And we have our first reaction. Now, the beauty of that is, having arrived at our first reaction using our compatibility equation, we still have available to us our static equation, and we can solve for the other reaction. And so I'm just going to move off to the right here to keep it nice and compact. And we're going to go sum of the forces. We haven't identified an axis, but the axial direction has to be equal to 0. We'll use up as positive. So now I'm looking at my original system. And so we have RA minus P plus RB I can substitute in for RA because we know that that now is PB over L. Similar to the other one, we can determine that our reaction at B is equal to PA over L. Now, there is a relationship between little a and little b and all of that, and that's useful in arriving at that simplified reaction. I'm just going to add a little note here, and you can see where that comes from. So there, I've just added that in, and you can see the algebra that goes into determining or simplifying the reaction at B. And that's it. So what we're really hoping to do here is to take what we saw in the theory and start to make it look a little bit more like we would apply practically. And hopefully that solidified what you're thinking. If not, you might want to go back to the little short lecture on either superposition if you had difficulty with that, or on statically indeterminacy. So hopefully that was useful to you, and we'll see you on the next one.